This is the second lesson of our third unit. Today we'll be looking at modeling the formation of ionic compounds. And my bell ringer for the day was write the symbol with its charge for your favorite group 2 cation. So this should be a review from our first unit, but cations are atoms that have lost electrons and have a positive charge. All of the metals form cations. If you think about it, all of the metals are on the left side of the periodic table, and those usually have between 1 and 3 valence electrons. So because they have between 1 and 3 valence electrons, they tend to lose electrons, giving them a positive charge. Anions, on the other hand, have a negative charge. Nonmetals are on the right side of the periodic table, and if you think about it, those have between 5 and 7, so they're looking to pick up extra electrons, so they have that full outer shell. So they all tend to have that negative charge because they have more electrons than protons. So here's a periodic table here, and if you look, all of the elements in red are metals. All of the elements on the right side in blue are nonmetals. So when we're forming ionic compounds, we're going to take one of the red elements and we're going to bond it with one of the blue elements. So an ionic compound is formed between a metal cation and a nonmetal anion. So for example, here we have sodium chloride. That would be an example of an ionic compound. We have a metal, which is in red on the left side, and then we have a nonmetal, which is on the right side in blue. An ionic bond is a bond formed between two ions by the transfer of electrons. So in our example here, if you look, we've got this electron here that is now leaving that atom, and it will move over to that other atom. And when we do this, this outer shell that was there disappears. And if you look, we have just 2 electrons in that inner shell. And if you remember, that inner shell only holds 2 electrons. So that outer shell is now full, so to speak. And that atom's cool because it has a full outer shell and it's stable. So again, atoms tend to want to move towards stability. So in this case, it's going to give up that extra electron. So we use Lewis dot diagrams, or LDDs, as like a visual representation of what's going on. These diagrams show the number of valence electrons. We represent valence electrons with dots. And when we draw these, we don't pair electrons until all 4 sides of the symbol have 1 electrons. So let's go through and let's fill in our table here. So our first element, sodium, has 1 valence electron, so I'm just going to put in 1 dot here. Magnesium has 2, so that last row, instead of putting another dot next to the existing one, I'm going to go up on the top here and fill it in. Aluminum has 3, so I'm just going to kind of follow the same clockwise motion. All right, silicon has 4, so 1, 2, 3, 4. Okay, now phosphorus is the first one that has 5, so we're going to double these up. So I'm going to go around first to make sure everybody has 1, and then there's another one. So very similar to the rule that we followed when we did orbital diagrams. We want to make sure everybody has, we want to make sure every side has 1 before we go back and give everybody a buddy. Okay, so again, I'm just kind of going clockwise and I'm filling these in to make sure that every side has 1 before I go back and double them up. There you go. There's a complete table. So again, the group number represents the number of valence electrons, and we're representing those with dots. All right, so the steps when we do this. First, we're going to draw the diagram for each atom. The second step is to draw an arrow to show the transfer of electrons from the cation to the anion. Then we're going to draw the ions in brackets with their charge. And we can check our answer by looking at the cation. There shouldn't be any dots on that when we're done. The anion should have a complete set of 8 dots, and the net charge should always be 0 because ionic compounds are neutral. So let's do an example here. So let's look at sodium chloride. So I'm going to begin by writing out my chemical symbols. So I've got sodium, which is Na, and then I have chlorine, which is Cl. So I've got 1 dot here on sodium because it's a group 2, and then I have 7 on chlorine, 4. I'm going to go ahead and fill in again, 2, 3. Okay, I'm going to draw in an arrow from my sodium atom to show that that electron is being transferred over here. Okay, and the formula when we write out the symbol is cation and then anion. And the X and the Y kind of give us the ratio we'll get to in a minute here. All right, so once we've transferred that electron, we're going to go ahead and draw kind of the final product here. So our anion, chlorine, let's go ahead and draw in. Now it has 8 electrons because 1 left sodium and is now on chlorine. And sodium lost an electron, so it shouldn't have any. So I'm going to go ahead and draw in my brackets. And that last step was to include a charge. So sodium lost an electron, so it now has a +1 charge. Chlorine gained an electron, so it has a -1 charge. Okay. Now, when I write out my formula, I'm going to write it out as NaCl. So our cation was Na, and our anion was chlorine. In this case, it was a 1-to-1 ratio, so we don't have anything else to add to this. This example is complete. Let's look at another example that follows kind of a different pattern here. We've got lithium and oxygen. Now, when we write these out, when we draw our diagrams, we want to kind of make these symmetric. So I'm going to draw out my oxygen, and I'm going to go ahead and include all of my dots here. So oxygen has 6 valence electrons. And notice how I drew my oxygen. I've got an opening on the left and the right. Now oxygen needs to have 8 valence electrons to be happy. And if you look on the periodic table, lithium is a group 1 atom, so it only has a 1 valence electron. So here's what's going to happen. I've got a lithium on the right side with 1, and I have a lithium on the left side with 1. And each lithium is going to contribute that electron, that valence electron, to the oxygen. So what's going to end up happening here, I've got lithium, oxygen, lithium. Oxygen has now 8 valence electrons. And let me draw in my brackets. So lithium is losing an electron. It'll have a +1 charge on both of these. Oxygen's gaining 2, so it'll have a -2 charge. And my formula is going to be lithium, oxygen. There are 2 lithium atoms here, so I'm going to write in a 2 after the lithium. And we are done with that example. All right, let's look at one more example. This time we're looking at magnesium and fluorine. So if you look at the periodic table, magnesium is a group 2 element. So let me draw in magnesium. And I'm going to put the dots on either side here. You'll see why in a minute. Fluorine has 7. And I'm kind of leaving that opening towards magnesium. You'll see why here in a minute. So in this case, the opposite is happening. Our middle atom is going to be contributing a valence electron to the outer elements. So when I draw on my my next step, my product, fluorine is going to have a full 8 on both of these. And let me go draw my brackets. So fluorine picked up an fluorine picked up an electron, so it's going to have a -1 charge. Magnesium forgot the G here. Magnesium is going to have a positive 2 charge because it lost 2 electrons, and my formula is going to be magnesium and fluorine. And since we had 2 fluorine atoms, or ions rather, I'm going to have a 2 after fluorine. So I provided a set of practice problems. You're going to work through those, and then anything you don't finish obviously would be homework. Our exit ticket for today was to draw a Lewis dot diagram for sodium and iodine. And that concludes today's lesson.